Okay, so we're going to start onto the KdV equation. So this is a super important equation, and it is something that we're going to study in detail a lot in the course. It's the most important nonlinear PDE, I think, and it's going to form the majority of the course. In some sense, it's going to form the middle third. It's the one we study the most. I shouldn't say the majority, but the rest of the course is quite linked together. So the first part understands by itself because we no longer have characteristics. We get into another different way of analysing these equations, and we look for travelling wave solutions and things like this. So let's just try and understand the equation. It has a really beautiful history, this equation. So John Scott Russell, who's quite a famous naval architect, he observed this very weird wave in a canal, and he built a system, an experimental system in his backyard and explored it and was able to reproduce this wave, and he called it a solitary wave. I think he gave it the name solitary wave, a wave that propagated by itself. And Stokes, who was the sort of mathematician, said these waves couldn't exist. And I suppose back in the day they didn't have iPhones to take movies of things. So they said that this wave didn't exist, and so there was some debate, and eventually Korteweg and de Vries derived this equation that you see here. Okay, and I've noted the 6 here is just arbitrary, but this is just the standard way to write it, and we non-dimensionalize it. We just put a 6 here, it makes it easier for us, so we can integrate twice, basically. It's 2 times 3. So this is the equation. They derived this equation and they showed that this is the equation that governed the wave that John Scott Russell had observed. And then the equation sort of lay dormant, and it was more of some sense of curiosity, but it became really important from the 40s onwards when the experiments were performed and that this was shown to have very remarkable properties. Maybe the 60s, this equation, some of which we'll touch on shortly. All right. So we're going to start out with this equation. We're going to look at the travelling wave solution. This is going to be a theme of what happens. So we're going to attack these equations in a few different ways. We're going to derive analytic solutions, we're going to derive numerical solutions, and we're going to derive these travelling wave solutions. So we're going to do take the 3 different approaches to solving these problems. So the travelling wave solution says that u is some function of x minus ct. Introduce a coordinate for x minus ct just to help us out. Zeta. Okay, and then the key point is that c is unknown. It's a variable in the equation, and we'll only get travelling wave solutions for certain values of c. Let's have a look at this. What happens if we substitute that in here? We get minus c times f dashed plus 6f f dashed plus f triple dashed equals 0. Doesn't seem to have led us terribly far. And by f dash we mean df d zeta. Okay, so there we are. We've got this far. So we can immediately integrate this equation. And what are we going to get? We're going to get minus c times f. This integrates to give us 3f squared. So if we integrate this again, we're going to get f cubed. That's the reason for this 6. F double dash becomes f double dash equals some constant a1. All right, so what do we do with this equation here? How do we analyse this equation? There's loads of different ways of looking at this equation. So I'm going to give you a couple here. Let's clear this page. All right, so this is our equation. Minus CF plus 3f squared. Now the constant's arbitrary, so let's just set it to be equal to 0 to make our life simple. And so we're just trying to find a solution. We're trying to find our travelling wave solution at this moment. So we can write this as d squared f d zeta squared is equal to minus dV/dF. So this is analogous. We're thinking about V as being the potential energy. So it's in a potential well. So this is a little bit weird why you would do this, and I'll just try and show you how it is. You wouldn't obviously think of this yourself, but this is the equation of motion of a particle moving in a potential well, which depends only on its position F. So zeta is like the time. This is Newton's second law. So if I integrate this, I get the potential must be given by C times F squared. Sorry, I'm going to make sure I get the signs right here. Minus C times F. There's a couple of minus signs, isn't there? This has got to go over to the other side. This is minus plus F cubed. So if I draw a picture of that, the potential well here is, I have a 2 here. Here's C over 2. Potential well looks like this. Whoosh. Didn't a great job drawing it. Comes up and it just touches here. Alright, so that's my V, this is my F, and this is my V. It's a bit tricky maybe to think about what's going on here, but this equation, the particles rolling around inside, it's a ball rolling around. So there's one solution that comes down here, rolls up and stops here and rolls back and forth. And if I plotted that in time, I get the F goes up and down like that in a wavy sort of way, right? That will correspond to that blue. So that is a solution, that's a travelling wave solution of this equation, of the KdV equation. There's a travelling wave solution that looks like that. There's the ball rolling backwards and forwards in this well. And there's another solution, a very special solution. There's the ones that come up here, whiz down and then just disappear off, and they are solutions to the equation, but they're not really travelling waves because they're not periodic and they go off to infinity growing. There's one solution that starts out here, the top of this point here, at t equals minus infinity, and it slowly falls, then rushes down here up to the other side and then comes back and then stops here and comes, so at t equals 0 it arrives here, and then it comes back and it arrives back here at t equals minus infinity. So what that looks like is it comes up, grows up, F reaches a maximum of C over 2 and then disappears off down like that, and that is the solitary wave. Of the KdV. Okay, that's the one that was observed by John Scott Russell. Okay, we're going to actually derive the formula for the solution. We're going to integrate. We're going to do that second after looking at and analysing it like this. But you can see here that kind of the way that solution is going to exist, there is going to be such a solution.